Yeah, so let's introduce Moustrou to you, who we got to give a talk at this doctoral day that we had to organize ourselves, and he will talk about exact semi-definite programming bounds for packing problems. Sharing his screen now, and I'm looking forward to it. Thanks. The floor is yours.
Okay, thank you, Felix. So yeah, thank you for the invitation. I'm very glad to open this ESR days. So yeah, when Felix asked me to talk about this project, so the first thing that I thought was maybe it's better to give like a general lecture about optimization bounds for packing problems. But then I realized that David was giving a talk in this workshop, so he already started mentioning a lot of things. So I can actually focus on exact optimization bounds, but still I want to give something a bit broader than just talking about our project. So I will just give kind of a general lectures about how, so why we do care about getting exact optimization bounds for packing problems and how to get them in general. So this will be, and then in the end I will focus on this project, which was a project with David, who gave a talk 3 days ago, and Maria Dostert, which is in KTH. Okay, so what will be the plan? So for the large part of the talk will be devoted to explain the title, basically. So first I will give like an overview of packing problems we want to tackle. So there are the sphere packings in our end, which are the things that David mentioned in the first part of his talk. So I will just give an overview of this, just to make a complement to David's talk. And also I will explain other kinds of problems which are a bit involved in the end of David's lecture, which I call local sphere packings. So kissing numbers, spherical codes, and I will explain these kind of things. Then also I'll try, so this will be also a combination of complement of David's talk and also optimization done so for spherical codes. So how do we, so this also very much related to several talks we had in this workshop, like about hierarchies of SDP bounds for independence numbers and this kind of thing. So I want really to give you the bounds we use in general for these problems, like for kissing numbers, for spherical codes, and also for sphere packings in R. Okay, so once this will be done, then we can focus on exact bounds. So the two things I would like you to understand today is first why we do care about getting exact bounds and not just some upper bounds on some independence number, why we do care to have sharp bounds. So the first thing is why, and the second is how to get them. So I'll give you a bunch of examples. Sometimes it's easy, sometimes it's hard. So we could see in David's talk that this was hard sometimes, but you will see also that there are some easier examples. And then I will focus in our context, so in our project, which was some kind of intermediate situation in which we have a numerical bound from the SDP, from an SDP solver. We assume it's sharp because it's numerically sharp, it seems to be sharp, but we still want to have an exact solution. So the question is, how do we start from approximate solution to an exact sharp bound? So the idea will be how to round this approximate solution to an exact bound. Okay, so this will be the plan for today. And by the way, I'm not seeing anything, I'm only seeing my slides. So I don't see the chat, I don't see anyone. So if ever you want to stop me, please stop me and shout. So don't raise your hand or don't write in the chat, but just stop me and shout. Okay, so first, let's just try to wake up, because now we are waking up earlier than during the other days of the week. So let's start with just motivation. So David gave us motivation for the sphere packing problems, but I think he forgot the most important one, which is a very motivation for these days. So if we want to keep social distancing between people, okay, so assume that for some reason, some random reason, we want to keep people far from each other. So, and we want to respect some 2 meters distance from each other. Then what we want to do, we want to deal with a large number of people. So the idea is how to arrange them in such a way that they are not too close to each other. So what does it mean? This means that if we draw spheres around everyone of radius 1 meter, then these spheres do not overlap. Okay, so this is exactly the sphere packing problem. So you want to put as many spheres as possible in such a way that you don't have any overlapping, and then you can choose your space. So this can be in Rn, this can be on the sphere, this can be on the box, whatsoever. So this is what I call in general sphere packing problem. Okay, so yeah, so this was just this motivation. I hope this is the last time I'm making this joke, and then next time we can meet in some workshop and we can forget this situation. But at least I wanted to make it one last time. Okay, so now let's discuss on the spaces. So in Rn, this is what David presented in the beginning of his talk. So now the space in Rn is Rn, the Euclidean space, and we want to pack as many spheres as possible. So what does it mean as many spheres as possible? In Rn, you want to look at the densest way. So you want to lose as few space as possible. Okay, so you want the gaps to be as small as possible. So this is solved in dimension 1, 2, 3, 8, and 24. So here we have the solutions in dimension 2 and 3. So in dimension 2, this is given by the hexagonal lattice. In dimension 3, by the FCC lattice, which is basically what we expect. Okay, so we could see also that David's motivation was violent with cannonballs, but yeah, here I prefer giving some food motivation. Usually, I'm more interested in food than in war. Okay, so basically in these cases, the solutions are what we expect. So in dimension 2, the arguments are mostly geometric. So by geometric arguments, we can show that those are the optimal solutions. In dimension 3, so this is what David was saying. This relies on computer assisted proofs. So this is the large proof by Hales, where, for instance, also Victor Magron, who is a member of Polynomials, was involved also during his PhD. And then in dimension 8 and 24, this was solved by other methods, which also rely on optimization bounds. So we will tell a bit more about this later. But this is basically all what we know for just sphere packings. And then also we know if we restrict our attention to lattices, so to regular packings, so where the centers of the spheres are shaped a lattice, then we know the answer in dimension 1 to 8. So we also know the answer in dimension 4, 5, 6, and 7. In dimension 4, in dimension 4, we expect this to be optimal and unique also, but this is still open. Okay, so this was this is the most standard problem of sphere packing. But then you can look at some other cases. So for instance, what I will call local sphere packings. So this will be compact sphere packings, finite sphere packings. So the main motivation for this is, for instance, the kissing number problem. So what does it mean? So the question is, I have one central sphere, which is here the blue sphere you can see. And the question is, how many spheres with the same radius can you put around the sphere, so touching the sphere in such a way that they do not overlap? So this is the same kind of problem, but on a different space. Okay. So then I will discuss this later, but yeah, you can really see this as a packing problem of spherical caps on the sphere. So this is really the same kind of problem, but the space is different. Okay, and here also we know the dimensions. We know the answer in dimension 1, 2, 3, 4. This case is known, and 8 and 24. And for instance, 8 and 24. This is also given by the same structures. So if you take the E8 lattice, for instance, so the E8 lattice, this is the infinite lattice. This is the best packing in Rn. And then if you just restrict your attention to the shortest vector of E8, so this will be points with the same norm, so they will be on the same sphere, and this will give you the optimal configuration for the kissing number. Okay, so the same structure gives you the answer and the unique answer to two different problems, and this is the same in dimension 24 with the Leech lattice. So these are very special structures. Okay, and then you have some variants of this problem. So yeah, first let's see how we write it down. Okay, so the way we define it, so the kissing number, so we try to maximize. So yeah, instead of looking at the centers here of the spheres, what I can look at is here just the projection I have here on the sphere. So also you can think of this as centers of spherical caps on the sphere. Okay, and once you try to pack, we try to pack spherical caps on the sphere. So what I can look at, instead of these centers here, I can look at those points, and what do I want to do? I want to put as many points as possible on this sphere, and then I have distance constraint. So now I don't want them to be too close. So what does it mean here to be too close? This will mean so that the inner product doesn't have to be too large. So I want the inner product between 2 points here to be at most 1/2, which corresponds with the cosine of this angle, which is here by 3. Okay, so I can write it. So from now on, I will call this a code because this is the standard name. So the maximal size of a code on the sphere, so points on the sphere, such that for 2 different points, they are not too close, and not too close mean and inner product less than 1/2. And then you can play with the parameters of this. So this is really from kissing number because you have the same sizes of spheres. And then you can play, for instance, with the sizes. So here, instead of looking at spheres of the same radius, I can play with the radius of the small spheres, and then this will have an impact on the angle constraint. So instead of asking that the inner product is less than 1/2, this will be less than the cosine of some angle. And this is here the angle I allowed between the two points. Okay, and this is what we call in general a spherical code. Okay, and also the question is, okay, what can be the largest side of the spherical code? Okay, so now we could play with the radius, and the other thing we can play with is the set of contact points. So for instance, instead of allowing contact points on the whole sphere, we can just say, okay, I just want points here to touch on the upper half of the sphere. So this is what's called the hemisphere. And then you have variants of this problem, which we call, for instance, the half kissing number. So the maximum number of points we can put here on this hemisphere with the same constraint as usual. Okay, and here, so what we will see a bit later is that this is a bit more difficult actually, especially for optimization bound, because we have fewer symmetries than in this case. Basically, we lose one dimension in the symmetry. So here, the symmetry of this problem is the orthogonal group of the full sphere, and here we have the orthogonal group of the sphere in 1 dimension less, because basically here we fix the North Pole, and then we can turn around this axis. So this is actually harder than the usual kissing number. Okay, so these are the kind of problems we want to look at. And now we have this connection with optimization. What we want to do, we want to see this as graph problem and independence number of graphs. So for the 2 situations, we can write a metric graph that will correspond to this problem. So we have the 2 sides, the Euclidean sphere packing. So this is in Rn, and the spherical code. So for the Euclidean sphere packings, the set of vertices will be the points of Rn. For spherical codes, the set of vertices will be the sphere. So if we think of the contact point, or the spherical cap, so the hemisphere, for instance. And then we have to understand what are the edges of those graphs. So in Rn, what will I say? I will put an edge between 2 points if they are too close. What does it mean that they are too close? This means that the distance between them is less than 2. So this means that if I draw spheres of radius 1 around x and y, these spheres do overlap. So I don't want overlapping. So I put an edge whenever I have a conflict between x and y. Okay, and I will do the same thing here. So what does it mean that 2 points will be too close on the sphere? This is what you say. This means here that the inner product will be too large. So the inner product will be larger than the cosine of the angle I'm looking at. Okay, so if I want a theta spherical code, I will put an h between 2 points on the sphere if the inner product is strictly greater than the cosine of theta. Okay, and in these 2 situations, what we want is we want to find the independence of these graphs. So those are infinite graphs. So it's I mean, it's already hard for finite graphs, but now we are looking at infinite graphs. So in this case, it's compact. It's a compact graph, but in this case, it's not even compact. And the idea is how to get bounds on those things. Okay, so for lower bound, this is like we have construction. So objects that come from like the E8 lattice, the Leach lattice that come from either from mathematics, like from number theory, for instance, for those structures. And we can see that they are better than the others. And the goal is, okay, let's show that they are optimal. And how do we show they are optimal? We need some upper bound. And so the idea for upper bounds is to use upper bounds from graph theory. So we have, for instance, we heard of the theta number many times in this week. So the idea, we have the theta number that gives you a bound for the impedance number of a graph. And then you have hierarchies starting from the theta number that will give stronger bounds. And the idea is to adapt this kind of bounds and this kind of hierarchies for these infinite compact or non-compact graphs. Okay, so here we have many papers for many people. So first for hierarchies for finite graphs and finite codes. This was described also in David's goals by Schreiber, by Monique, and also we can adapt like things from the Lasser hierarchy. And then you have adaptations to the infinite case. And for instance, there is a paper by David and Frank about these things that give really a unified point of view on those things, which is very interesting. Okay, but now today I want to focus really on the bounds we are in this case. And for instance, I want to tell you about the 2-point bound and the 3-point bound. Okay. So let's just describe, so this will be an analog of the theta number for this kind of graph, but I want to forget about the theta number point of view, and I just want to give you the bound. Okay, so just the two ingredients that are important in this case that already appeared within this week. The first one is like we have 2 points, so this will be based on 2 points constraint. And instead of representing a couple by all the coordinates and so on, now we are on the sphere, so the only thing, we want to use the symmetry of the sphere. So we say now a couple of points on the sphere. This is just determined by the inner product. Why? Because basically up to symmetry, so you have all the symmetry of the sphere. You can assume that x is just the north pole of the sphere. And then the only thing you want to know up to symmetry is what is the distance between x and y, and this is just given by the inner product. Okay, and now if you want a spherical code, then this inner product will be 1 if the 2 points are identical. And if not, then we say that the inner product should be at most cosine of theta, so it has to be between -1 and cos theta if they are different. Okay, and then the second ingredient is also something that appeared during the week. These are the Gegenbauer polynomials. Okay, so this comes also from kernel theory. I don't want to go into these details, but the only thing I do care about for the proof I will show you later is that whenever I have a finite configuration of the sphere, if I take the sum over all the pairs of points on my set of the Gegenbauer polynomials evaluated at the inner product, this is really positive. So this comes from the fact that they come from a kernel, from harmonic analysis of the sphere, but the only property I need now will be this one. Okay. And now, so with these two ingredients, I can show that I can get bounds on the size of spherical codes. So now I assume that I have a polynomial. So the first condition will be that it will be written as a positive linear combination of the Gegenbauer polynomial. And the second is that I'll hold the interval of possible inner product. I want f to be bounded above by -1. And if I have a polynomial, so the claim here is that if I get a polynomial with satisfying these two conditions, then it will give me a bound on the size of a theta spherical code. So let me tell you the proof. So this is basically one line. So if I take a spherical code, and then I want to compute this sum. So I want to compute the sum of f of x inner product with y over all the pairs of points in the code. And I will compute this sum in 2 ways. So I will bound this sum in 2 ways. So first, I just replace f by what it is. So now I have a double sum. And then I just swap the sums. And then I have the sum of alpha k's that are non-negative times the sum of the pairs of the Gegenbauer polynomials evaluated at the inner product. And this was the only condition we needed. I told you we needed for these Gegenbauer polynomials. This will be non-negative. So non-negative, the alpha k's are non-negative, so this whole sum will be non-negative. Okay, so this is for one side, and then let's see on the other side what's going on. Now I have this sum. I will split this sum in 2. So first, when the points are the same, so if x equals y, so this will happen exactly the number of points, so coordinate of c times, and then I will have f of 1 when the 2 points are equal, and then I have the sum where the points are in the spherical code and different. And what was the second condition we had here? We had the condition that that on if I have 2 points in the spherical code, then f of x dot y will be less than -1. So here I can bound all the term of the sum by -1. So here I have continuity of C. So what will be here -1, and I have the number of pairs, which is C -1. So in total, I have this bound here. So now I forget about everything which is in the middle. I just take the left-hand side and the right-hand side, and this tells me basically that here this thing is non-negative, and so the continuity of C is at most f of 1 plus 1. So whenever you give me such a function, f of 1 plus 1 will be an upper bound for the size of spherical codes. Okay, and so then the goal and the game will be to optimize over all such functions. Okay, this will be really the idea of the 2-point bound. Okay, so this is exactly what I'm writing here. So now I can write it as a linear problem, as a linear program. So I want to optimize over all the possible non-negative linear combinations of the Gegenbauer, such that here this will give me the bound, and I want this condition that f of u is less than -1 for every u in the interval of possible linear products. So really the idea is that I am optimizing over all the functions of this kind. Here I look at all the functions of this kind, and I want to find the best one that will give me the bound. Okay, and this is a linear programming bound, even if in practice, if we have a large such bound and we have here these non-negativity conditions, we might have to use sum of squares, and then we can compute it with SDP. Okay, so this is really the idea of the 2-point bound, and I will be a bit faster for the 3-point bound, but basically the idea is really the same. And instead of looking at pairs of points, I will look at triples of points. So here in this case, instead of to represent the triple, now I will need 3 coordinates that will be the 3 different inner products between the points. So basically you can assume that the first point x here is the North Pole. So then you have to decide where are x and y. So what will be their distance, y and z, sorry. What will be their distance to x and y, to x. So yx and then zx, and then you need to understand what is the distance between y and z. Okay. And then you have all these couple, and then you have the condition. So either they're equal, and so this triple will be 1, 1, 1, or 2 of them are the same. So you have 1, 1, and then u because the other inner products will be the same, or they will be distinct and they will be here in this domain. And basically this domain just tells me they have 3 points on the sphere and they correspond to inner products. This is a condition from a gram matrix. Okay, this is not very important. So this is the first ingredient, and the second, I want a generalization of the Gegenbauer polynomial, but in this time, I won't have just polynomials, but I will have matrix polynomials. So matrices in which the coordinates will be polynomials in 3 variables, and I have the analog of the property that was important for me before. The analog is here, that now if I sum these matrices for triples of points in a configuration, then this will be now not non-negative, but the equivalent of non-negative for matrices. This will be PSD. Okay, and then this leads me to the same kind of bound. So this is what we call the 3-band bound here. So now instead of optimizing over one variable polynomial function, you will optimize over 3 variable polynomials that come from this. But still like before, we are trying to find the best function. So now the shape is different, but the goal is to find the best function. So here sometimes when I present this, I think I get people confused, because some people are just thinking we're using, because now I'm saying that we have semi-definite programming bounds for using sum of squares. So we do have some sum of squares conditions here. So we have some SDP matrices coming from the sum of squares condition, but we have some other SDP matrices appearing here. So we have really 2 kinds of SDP variables in this program. We have the SDP variables for the sum of squares, but also the SDP variables for the function. We don't have yet the function we want to prove it's a sum of squares. So first we need to understand the function and make sure that it's not negative or where we want. Okay, so this is the 3-band bound, which gets back to Frank and Christine Bachak. Okay, so just to recap what we have for spherical codes. So for instance, for the kissing numbers, we have the 2-point bound, which is the LP bound. From now on, I will call it the LP bound, and the 3-band bound, which is an SDP bound. So this is really for spherical codes when I have the whole sphere as the set of contact points. And what I told you before is that now if you look at spherical in spherical caps, so for instance in the hemisphere, so if you don't allow contact points on the whole sphere, then here you cannot apply the 2-point bound because you don't have enough symmetry. So what you can do actually, you can adapt the 3-point bound by fixing one of the points to be the North Pole, and then this will give you a bound which is very much like the 3-point bound for spherical codes, but actually we have to think more of it as a 2-point bound. And this is also an SDP bound. Okay, so for this kind of problems, we don't have an analog of the LP bound, and the first bound, so kind of this first step we have, will be already an SDP bound. Okay, so this was for what I call the local sphere packings, and just to show you the analogy with what David was telling us on Tuesday. Here I just recap the bound David gave us on Tuesday. So this is now the LP bound, so the 2-point bound for sphere packings in Rn. And you can see that this is very much the same kind of bound, right? So we also look here for this optimal function. We want a function such that, so f of 0 will give me the bound on the density, and then I have some constraints, some non-negativity constraints. So here I have non-negativity constraint on f, but also on the Fourier transform. Okay, but it's really the same kind of flavor, and I just re-put here. I don't go in detail, but this is just copy paste from what David was telling us. You can see that this is basically the same kind of argument. So now here, instead of having this double sum argument, I have this Poisson summation formula, but basically the ideas are really the same. So you really have, this is really analog for in the non-compact setting of the 2-point bound. Okay, and you also have the analog of the 3-point bound, which is very recent, and this was exactly the first part of David's talk. Okay, so the strengthening of this bound. So and if you look at the bound, so I don't re-put the bound here, but you can see also that you have this condition which smells like the 3-point conditions. Okay, so this was the first part of the talk by David on Tuesday. Okay, maybe a question so far before we go to exact bounds. And just for me time to drink, so if you have questions, please unmute yourself. One, two, three. Okay, no question. So the question, why do we need about exact bound? Okay, so for density, we can understand now why we need exact bound, because basically we want to compute the exact best density. So if we have an approximation, this won't be enough. But like for spherical codes, we could say, okay, well, assume I have a configuration with n points, and now I know that this independence number will be an integer because this is the size of a set, right? So whenever I have a bound which is less than n plus 1, okay, this tells me that my code is optimal. And we can say, well, why do we care about exact bound? Whenever I have something which is close, even 0.5 close from the optimal value, then I'm fine. I know that my code is optimal. So in this case, you don't even care so much about the numerics because it's fine to have approximation, and you can. It's not so hard in this case to prove that, like to control the error to make sure that you don't go one above the optimal solution you have. So why do we care about sharp bounds? So first, the first question, this is also some motivation that came up during the week, is that first we want to understand in which step of the hierarchies we do find the independence number of the graph, right? So this is really the optimization point of view. You want to know, okay, at this step, I know I found the independence number of my graph. And also from a geometric point of view, and this is why I tried to convince you afterwards, is that from a geometric point of view, whenever you get a sharp bound, then you get some additional information on optimal configuration. So if you get an optimal function, then we'll get information on geometric information. And you can prove, for instance, that the candidate you have, this will be a unique configuration, the unique optimal configuration. And so, for instance, then you can prove the uniqueness as optimal configuration of several structures. So for instance, here, this is a spherical code. So in dimension 3 for this angle, which is ugly, but actually you can prove, and this was already proved, but only with geometric arguments, that this is the unique such spherical code in dimension 3. Okay, so you have to imagine that all those points here are on the same sphere. And also, like for so we know that E8. I told you that this gives us the best kissing number configuration in dimension 8. And now, if we stick our attention to the hemisphere, you can also prove that this is optimal. So here you look at the configuration of the whole sphere. You just put one point at the North Pole, and this give you a configuration of 183 points on the hemisphere. So Bachelor and Valentin with SDP bounds could prove that this was optimal. But the question is it unique? Okay, so this was our first motivation for this project with Marie and David. Okay, so now I want to tell you what do we get from exact bound. So I just re-give here the bound. So this is the linear programming bound. And I assume that I have a feasible solution, which gives me the optimal value. So I take the optimal function. This is what I will come from now on, the optimal function. So I have the optimal function that can be written as a non-negative sum or combination of Gegenbauer polynomials, and this will give me exactly the optimal value. Okay, and now I assume that this is sharp, and then I have an optimal configuration. So what does it mean? That I have a configuration, so a code C, where the coordinate of C is exactly m star. Okay, so now if I get back to the proof, what did I have in the proof? Basically, we use at 2 points. Okay, so we use at 2 points here. We had some inequalities here. So in this case, we use this inequality, and in this case also, so we had this inequality. But now look, here we have this m star minus c, but if m star is sharp, and here we have a configuration with m star point, then here this will be 0. Okay, so I have 0 on the left-hand side, 0 on the right-hand side. So what does it tell me? This tells me here, and this is what I will call the complementary slackness condition, that here the inequalities I used have to be equalities. And so now this will give me information on an optimal configuration. So if I have an optimal configuration, so this sum has to be 0. And since it's a sum of non-negative things, this thing has to be 0 whenever this coefficient is not 0. But more importantly, my optimal function, we know that we get some information on the roots of the optimal function. So the roots of the optimal function will be basically the possible inner products in the code. Okay, so I know that for every pair of points in the code, the inner product would be a root of f star plus 1. Okay, so this gives us information for the optimal configuration, but also the other way around. So yeah, this is what I was saying. So the inner product will be root, but the other way around, this also gives me the information on the optimal function I would like. Let's assume I don't want to do numerics, but I just want to solve this linear program from scratch. This gives me some information on the function I want to look for. So let's see. For instance, now I will give you the example for E8. So we will show now in this slide that the kissing number in dimension 8 is exactly 204 points, and that E8 provides the unique optimal configuration. So I know that this gives us a configuration with 240 points. And I want to show this is optimal. So let's try to guess the function. So now let's look at the inner product I have in this configuration. If you look at the inner product in this configuration, you have very few possible inner products. You have only 0, plus, minus 1/2, and minus 1. This is very few for if you just think of random configuration of the sphere. You might have much more inner products. But here you have only this one. So what does it mean? For instance, think of the best function you could have that would work. This would just be the function with those roots. So we look for a function of this form. So let's start with this one. So I just take the polynomial where I have roots at the inner products. Okay, but it's not the only condition, right? We also have the condition that this has to be less than 0 for every u between 1 and 1/2. So here this doesn't work. What can I do to fix this? I just can multiply here I can just double the multiplicity of those two roots. So here I add squares. And now my condition that f star plus 1 is less than 0 between -1 and 1/2, this is satisfied. Okay, and what is the other condition I need to have? Okay, I want this function to be optimal, so I want this value in 1 to be exactly 240. So I just rescale. So this is the same function that I rescale in such a way that here in 1 I get exactly the 240. So this is the first function I could look for and pray for it to be optimal. And actually it is. But now the only thing I have to check that this is indeed feasible. So I have to check that, and here I won't give the coefficient, but you can check. I have to check that this one is indeed a non-negative combination of the Gegenbar polynomial. So you can find coefficient, and then this tells you that this is a feasible, so this is a feasible f, and so this tells me that the configuration for me is optimal. But now, if I take another configuration which has to be optimal, now this tells me that the inner product have to be roots of those things here. So now the inner product for any optimal configuration, they have to be among 0, plus minus 1/2, plus minus 1. And this is a very strong condition. Actually, this will tell me with a little bit of geometry. This tells me that there is a root lattice. And then once you have, you just have to look among the root lattices, what are the size of the minimal vectors. And actually, you have very few root lattices. All of them are very well known. And you know that the only one with 240 points on the first level, this is E8. Okay, so this tells you that the configuration is optimal and unique. Okay, and this comes from the optimal function in the optimization program. Okay, so now let's try to do the same strategy. So this was already appearing a bit in David's talk, but now you can see the connection, I hope. So if we try to do the same thing, so we have also this complementary slackness. So whenever we applied inequalities, now we have to have equalities. So now we're looking for a function which is for such that for every non-zero point here, because basically here we just said that we just replace the sum by just f of 0. So this means that f here has to be 0 on every point, every non-zero point on the lattice. Okay, and this is also a very strong condition. And for instance, here you can see that you have infinitely many zeros. So this cannot be a polynomial. And more than this, so this is what David was explaining, that now if we look for functions of this shape, so in practice we have to parameterize with polynomials to solve solve numerical programs, so SDP in practice. Then we optimize our polynomial. So this tells us that with this method we can never get a sharp bound. We can only have approximation of optimal functions. We cannot find optimal functions like this. So this is why we need something else. And this something else came from Marina Wiazowska, and the idea was so she did construct an optimal function for this problem by using modular forms. Okay, so and this is related to other problems in harmonic analysis. So you have this uncertainty principle of and also this question of finding eigenvalues for the Fourier transform and so on. But this brings some hard analysis issue, and that can be solved here with modular forms. So this strategy works in dimension 8. This is what he first proved, and then together with Kohn, Kumar, Miller, and Radchenko, they can apply the same kind of techniques in dimension 24. And this is also conjectured to work in dimension 2. This strategy, so the bound seems to be sharp, but still this is still open. People could not find the function after. Okay, so just to recap, so we have many examples for spherical codes where LP works. So we have just one variable polynomials, and this is not hard to deal with. We have some examples for LP sharp bounds for the Euclidean pathings, but now finding the optimal function, this is hard, and this cannot be done directly from the numerics. So numerics give you information, right? You have an approximation. You can try to interpolate so it's the other way around of approximation, right? You have the approximation and you want to find the function. This is kind of the other way around, but it's difficult. And the question is now, okay, now, so for instance, for spherical codes, do we have cases in which the LP bound is not sharp, but the SDP bound is sharp? Okay, so this is, for instance, why David was wondering if the 3-point bound I have for lattices, is it sharp in dimension 4, right? Because for the LP bound it's not, but maybe it is for the so we're looking for example in which the first step of the hierarchy doesn't work, but the second gives you the exact answer. And for spherical codes, actually, in this case, there were several cases in which the SDP bounds seem to be sharp, and the question is, okay, how can we prove that? But in this case, we have three variables polynomials. You have SDP matrices. I mean, the optimization programs usually they're much bigger than the ones for the LP bound. So this is much harder to guess the optimal function. We can apply the things I told you for E8 and for the 2-point bound. So this is what we try to do, and what we did now with David and Maria was to give a general framework, so like a strategy to use the numerical solution and to find an optimal. So you don't have uniqueness of the optimal function, by the way, but to find an optimal function from the numerics to get the geometry. Okay, and what we could do, so we could recover some examples. So either examples that were done with geometry or without SDP bound. So here the better one. So this was also spherical code, and this was proved optimal by Bashak and Valentin by showing that the SDP bound was sharp. But here it was a mix of computation and guessing. So first they started guessing some coefficients. And so this was quite technical, and here with our approach we just recover it a bit more directly by applying our procedure. So we could get this bound exact also for the square antiprism. So this was the configuration I told you I showed you before, this 8-point configuration in dimension 3. So here Bashak and Valentin, they conjecture the bound to be optimal, to be exact, but they couldn't prove it. Also because here in the solution was not in Q, but was in the quadratic field. So here we could apply our method to prove that here the bound is sharp, and we could prove also this problem with the uniqueness of E8 as a solution for the hemisphere problem in dimension 8. Okay, so we just have several problems that fall into this framework. Okay, so and now I will spend like the last 15-20 minutes to tell you about our project, but maybe that's a good time for questions. So this was really the general part of the talk, and I will focus more about our project. The question? Okay. Okay, so now, so you can forget about the bounds and just say that now we have an SDP. So the way I like to think of it, especially for this kind of things, so we have the objective value. So the objective function, this will be just a linear objective function. Then we have some linear constraints, and then you have some PSD constraints. So here I just think f of just one large vector. I put all the coordinates, and so I just think of one big linear system, and then I have these SDP conditions given by blocks. Okay. So I have these two kind of condition, and I would like to solve this exactly. But in practice, the programs we have, they are big. We have many unknowns, many constraints. So it's hard. It's impossible for this kind of programs to get the exact SDP. So you have some approaches to solve SDP exactly, but this works only for very small examples. So for larger problems, we just have approximate solution in floating point that you get fast, and the goal is how can you turn this approximate solution to an exact bound. Okay, and here our case is a bit special, right? Because we have some guess on the function we want. So we want, for instance, a function with rational coefficients in some case, or at least something which is in the same field as the definition of the problem. So in general, you don't have any insurance of this. Like even if you have an SDP which is defined over Q, then and this was proved by Nierenstad and Stromfels, that the optimal solution might be in much more complicated algebraic field. Okay, but in our case, we really expect to have an optimal function, to find an optimal function, an optimal polynomial with coefficients in the field given by the problem. So Q or for some examples, like for the spherical code, like in Q of square root of t. Okay, so we can apply our thing to Q, to rational one, and to quadratic field. But this is really a special case where we do expect to have a solution in this field. So I will just tell you how we do for our rounding method, but over Q, and the strategy is the same of over Q of square root of d. And so that basically we double the number of overheads. So first, in our case, we know we have some candidates, right? So we want to show that the configuration is optimal. So we know the optimal value. So for instance, we don't have to optimize. We just include this objective as a constraint, and we look for a feasible solution. Okay. Also, we can add some further So the goal is to put as many constraints as possible. We can use the complementary slackness. We know that the function we look for, it has to vanish at the inner products in the configuration. So we have a feasibility problem in this case. Then of course we want to reduce the number of variables, because the fewer variables, then the easier it would be to round. So we use symmetries to reduce this number. So for instance, for the hemisphere, we can, so we don't have so many symmetries in this case, especially for the hemisphere. We just have basically the XY symmetry, but this already help us reducing the size of the problem. We solve it numerically, so we use high precision. So as David was saying, usually we use SDP-GMP for solving these problems, and we get something which is approximate. So what does it mean to be approximate? This means that the linear problem I have is almost solved. So if I look at x star minus b, this will be almost 0. And the blocks here will be and the blocks will be almost PSD. What does it mean to be almost PSD? This means that the eigenvalues will be almost non-negative. So either they will be positive and we're fine, or they will be close to 0, but close to 0. Unfortunately, with precision, they can be negative. And this will be the problem, that we might have negative near 0 eigenvalues. And the problem will be to deal with this. So the first naive thing you want to do is just, okay, to fix these linear conditions. So the goal is to find some x which is close to the numerical solution, such that the linear system is satisfied. So how can you do this? You just solve the system as you would do in first year linear algebra. You just reduce it, and then whenever you have a free variable, so you use back substitution. And whenever you have a free variable, you take a value which is close to what you have in the numerical solution, and you just solve your problem. So you have an exact solution of your problem, which is not so far from the approximate solution. So now you know that the linear system is satisfied. But the question is now, okay, now what about the PSD conditions? Are the PSD conditions satisfied? Well, in general, not actually. I mean, sure, there is a case in which it's easy. So if the first block you don't have any 0 eigenvalue or close to 0 eigenvalue, then if the values are positive and far from 0, then they will, even after perturbation, they will stay positive. They will remain positive. But unfortunately, this is not the case in general. So the idea is that we don't have enough constraint, and the question is how to do when we have near 0 eigenvalues. So actually, the idea is to say, okay, if I have near 0 eigenvalues, they have to be 0, and so I want to force them as being 0 eigenvalues. So I want to force this thing 0, and then I would just stay with positive eigenvalues, and when I use this perturbation, I will stay PSD. So how do we enforce more constraints to force these 0 eigenvalues? So the first idea is to use complementary slackness. So here we have complementary slackness of roots, but you can add also some complementary slackness condition on the derivatives, and sometimes this is enough. So for instance, in the paper by Kahn and Wu, so this was the 3.1 for codes in projective space. Here this was enough actually to force the 0, and then you can use the naive rounding, and this works. And actually the hope at the beginning of this project was that this should work as well, but it was not the case. So that's why we had to deal with something more general. So the question is, how do you force all this 0 constraint? And so the idea would be to guess the kernels. So the idea will be and here again we use the assumption that we will find a solution over Q in our case. So the intuition is that, yeah, there have to be some reason, like the complementary slackness or maybe some other geometric condition we don't think of, that force the kernels to be nice. So we take a block, and so we have this almost PSD matrix. We compute the kernel because we only want to deal with the kernel, something in high precision. So we get ugly numbers. And here I just give the example with one variable, just to give you the idea. So we have these ugly numbers, and we want to turn them into something nice. So for instance, here we just divide by one of the coordinates and say, okay, yeah, this looks like something very nice. I just can run them, and I guess the nice rational numbers I have. Okay, so this is just the idea for one vector. And then once I guess this vector, then I want to force it to be an eigenvector to be the kernel of my PSD matrix, and this gives me additional constraint that I can put in the system. Okay, so this is really the idea, and now I want to generalize this to higher dimensional kernels. So in this case, it's harder, right? Because if you have ugly combinations of those bases. So if you divide by one coordinate, you won't get something nice. But the idea is to detect some combinations of those things, some equations that are satisfied by those things. So to do this, you can use LLL, which is actually one of the applications of the LLL algorithm. Use LLL, and if you apply LLL to these vectors, they tell you, for instance, that here if you do -1 times the first coordinate plus 3 times the second minus 2 the third, or with these vectors, then you have something which is very close to 0. So we say, okay, this condition has to be satisfied by my vectors. Then you look for another combination, and now you have, okay, we have two vectors in dimension 4, so we only need 2 equations. We have the equations, and now we can find a nice basis of this kernel, and we say, okay, wow, this is very nice, and now I want those vectors to be I want to force these vectors to be in the kernel of my block BI when I round. So okay, and this gives us some more additional linear constraints that I will put in the system. And now I hope that when I do this, then I have only either exactly 0 eigenvalues or something that are positive. And when I solve the system, then I will be fine. And this is what's happening. So first I compute an approximate solution, so numerically. So just to recap here, this is the full method. So with all the steps. So first I have the approximate solution. Then I look at the blocks. I compute the kernels with what I told you before. I have some expected kernels, so I have a nice basis. Then I include them in the linear system. So I have a new linear system which is larger with these vectors forced to be in the kernels of the BIs. Now I use row reduction, and I can solve it with back substitution with the first method. So now after this, I know that the linear constraints are satisfied, and the last thing I have to do is to check that the blocks now of the rounded solution are PSD. So now I check that I have a feasible solution. Now, since the linear system is satisfied, I know that the objective value is the one I want, and this gives me the function I want. Now I do have the solution. And now it's not completely over, because the last thing I have to do is to make sure that the function I get is sufficient to prove uniqueness of my configuration. So now after this, for instance, I will have my polynomial of 3 variables, and I have to check that this will give me the information I want. So first, that I want to check that the possible inner products, so the complementary slackness condition, are only satisfied by the inner products in the optimal, in the candidate I have. So for instance, 48, that I cannot have more inner products than the one I have. So for instance, we use some Sturm method to understand where are the zeros, to make sure that we have enough and we don't have more zeros. Then, so this is something I didn't mention, but this will give you more information on the geometric configurations. What are the possible inner products, and the 3-point distance distribution? So it tells you how will be distributed the triangles in your configuration, for instance. So these are really some combinatorial information on your optimal configuration, and then you use a little bit of geometry to conclude, to make sure that you cannot have anything else. So for instance, for this square antiprism, then we need like maybe 3 lines of geometry compared with the several pages of geometry in the initial proof. So after the geometric part of the proof is much smaller than in this general than the standard proofs for these statements in general, that you have many different cases to check. And here, after this, once you know the inner product, this is much easier. Okay, and yeah, I will stop here, and we have little time for questions, and then we can have coffee before the next talk. Thank you very much.
Very nice. Thanks a lot. It was a nice talk.
And now I'm not hearing anything.
Did you hear me? Can you hear me, Philippe?
Now, yes. Yeah, now, yes.
I was just thanking you for the talk. So
okay.
Let's wait to see if there are some questions, maybe. Olga, we can't hear you.
Okay, neither here or see anyone. I don't know if it's on purpose or not.
I think there is a question, but the microphone is not working, so I think she's typing it in the chat. And maybe Daniel.
I think it's working now, right?
Yeah, we can hear you now.
Daniel can ask. Daniel can ask, then I will ask.
Okay, just a quick question. The rounding algorithm seems to generalize to more SDPs. Do you have by any chance code available? Or is it very easy to implement?
Sorry.
The rounding algorithm to get an exact solution seems to generalize to other SDPs. Is there code available for it?
Yeah. Yeah, this is you can find it on the archive version of the paper. You have a link to the code. I'm not sure this is completely up to date though. David can confirm or not confirm, but yeah.
Okay, yeah,
it is.
Everything already. Yeah, thank you for the talk.
Thank you.
Thank you also for the talk. So I had just a specification question. So it seems that you need to, let's say, do several steps, which a little bit depend on guessing. Can it actually be, let's say, that the procedure doesn't converge? So how heavy it is dependent on the guessing? Or even if I have, let's say, a relatively good guess, can it be that still I won't find the solution? Did you have such cases?
Yeah, so we had to play a bit with parameters when you use LLL, for instance. So we have a part after guessing. So when we guess equations, I don't know what you're saying now, but
I see the slide.
Yeah. So here, when you guess equations, here we do have to check after we compute the kernel. We do have to check that we did find some things that are in the kernel. So after we find these vectors, which we looked at, they're very close from being in the kernel of the numerical solution. But we did have to play, like the first time we tried, the parameters were not good. Like either the precision, I don't remember it was too large or too small. But first, either we couldn't find any equations, or the vectors we were looking at were not canonical. So we found things that were. So we had to play a bit on the parameters. So we're a bit lucky here that we're a bit lucky that the basic
crucial step that you need to find. That if you can find them, since that, then it will. I see.
Yeah. It's more of a heuristic. You try to find them, and in this case, we're lucky because we find them. Okay. But in general, you have no. So first, you don't have to find them over Q. So here in this case, we hope to have them over Q, and then also they are nice enough. I don't know how much this is like dependent. So this was also one question we had in mind, but we never really thought of it. So this condition, do they come from geometry or not? Are they very specific, or is it just luck, or is it just that we recover some things that don't come from geometry? Yeah.
And this problem is one of the ones that you mentioned at the beginning, or? Yeah,
no. This is the variant of the kissing number for the hemisphere. But here, okay, I just got the vectors. We don't have. Yeah, this is not 4-dimensional. I just took some pieces. I think we have something with 100 coordinates or so. Like I think this was we had some kernels of dimension 20 in for several yeah, this was much bigger, but this is just to present the idea. This is not extracted for I should have mentioned
that
this.
Is very nice, then.
The kernels are they are much bigger, but the equations are really nice though, and they are sparse, and but the equations are sparse. So this is also why we were thinking that maybe there are some they come from somewhere geometrically that we don't know.
Yeah, then that's also something interesting to look at. Yeah, I see. Thank you very much for the answer.
You're welcome.
And the presentation.
Okay, so it seems that that was it with the questions. Once again, thank you very much for this nice talk.
Welcome.
And yes, so I will make sure to check out the code on the archive.